No, the 2 cancels out. This is NIX.
Yeah. Yeah. But you get pi ni plus 2 nx I, which you can pull the I out. So you get pi n plus xn times I, all times I.
Yeah. And, no, what you got there, NI times 5 plus 6.
Okay, so ni times pi plus x dx. Now, I think what he's claiming, I believe, I don't know if he said this or not, but I think the claim is that, I think he'd like to claim that, you know, e to the 2 pi I n x over a is complete orthonormal system in L20A, yeah? I mean, I think that's what he's getting at by writing this here, right?
Yeah.
So if that's true, I feel like that simplifies. That's bugging me. Look, this has got to simplify, guys. This is e to the INX, which is what I'd like to see. Uh-oh, we lost Audric. INX.
Oh, I'm here, sorry.
You're fine, Audric. So like, you see up here? INX, right?
Well, EIN pi.
Now, I haven't been able to see the right hand of the board, but I have been imagining it.
Oh, I'm sorry. Let me shift you over here. E to the IN. What is e to the IN pi? Do you guys know what that is? Here, I'll make it up close and personal for you.
Thank you. So yes.
So
well, e to the 2 pi I mean, that's just 1.
that is cosine n pi, is it not?
Oh.
Which I was just telling my Calculus 2 class the other day.
Yeah.
Is actually, yeah, this is minus 1 to the n. So if I read this more carefully, does he still have a sum over the integers here? Or did he actually drop the integers and just go to negative infinity to infinity, huh? Yeah. Golly. Oh. Huh. Huh. Yeah. Well, anyway, I think you can see that we can get from that formula to this formula practically. I feel like this is, I think this is the rescaling he's talking about. I mean, you're right, Audric, he spends more time in section 3.5 talking about it, but there, all of a sudden, we're not going 0 to a, we're going minus pi to pi, right? And
Yeah.
so, all right, anyway, hey, we've done the legwork here. We can use this later to finish the thought if we need to, right? All right, let me move on here. I'll go a little bit longer today if it's okay with you guys, because than I would usually do on a Wednesday, because I've got a student taking a test, and he dislocated his wrist, I think, yesterday, and it's his writing hand. So I have just try to buy him another 10 minutes here with our examples, and I'll just eat faster when I get home.
We do have a definition to wrap up. Oh, no.
Yeah, that's what I wanted to get to. Well, tell you what, let me just read for a bit here rather than writing everything out, yeah? So next up, he gives a sequence of functions, 1 over root pi, cosine, sine, cosine. I guess I can write it out. So,
You gotta move me.
what's that? Oh, oh yeah, he's moving you. Sorry, Audric.
All good.
So the other orthonormal sequence is like this.
Thank you.
Is that good? Go.
To the camera. Yeah. Well. Yeah. That's good.
So you notice here, instead of using the this is an alternative orthonormal sequence for L2, right? And he gives more of the details, but ultimately it really just rests on this. E to the I nx is what? It's cosine nx, right? Plus I times the sine of nx. And it just turns out that sine and cosine are perpendicular functions, right? These are orthogonal functions. And so you can play these games. You can replace the orthonormal sequence we talked about in the previous example with this one. And then his next example, L2. See, now it's starting to upset me. This one. And here he claims you can do. See, has he written down the inner product for this thing? Am I just forgetting it? Surely he wrote it down somewhere. What's the inner product on this guy? Do you guys know? This example here. So this space, what's the inner product that he's using?
Around what? L1 or L2?
L2.
L2, the inner product is defined by the integral from minus infinity to infinity of f of x times g of the conjugate of g of x dx.
So this is the inner product of f and g.
Yeah.
But we're on L2, 0 to pi. There's got to.
This is for R.
I'm looking for what's the inner product from for the L2 0 to pi space.
Well, would that just reduce interval from 0 to pi? Would it be 0 or power?
Ow.
Okay.
Yeah, I'm okay. It's just my knee. Didn't like the chair. So my suspicion is that it,
I see one for minus pi to pi.
I mean, I'm guessing it's 0 to pi, 1 over pi. That would be my guess. But, well, anyway, let me just put a, question mark here since we're not sure yet, okay? I wonder if he's, well, anyway, I don't have a photographic memory of everything we've done, so, you know, I don't want to judge him, right? Okay, so next example, he talks about these Rademacher functions and the Walsh function. And these are the sine of 2 to the m pi x, where the signum function is 1 if x is positive, 0 if x is 0, minus 1 if x is negative. He says these form an orthonormal system in L2, 0, 1. Yeah, this is some kind of dark magic here. I don't know. This is weird. What on earth are these things? Curious example. This Rademacher functions. And he proves that they're orthonormal here on page 117 to 118. And then he uses those to construct these Walsh functions, which also form a complete orthonormal system. He has graphs of them on page 119. They're kind of, they're reminiscent of some of the things we've seen in the step function constructions, yeah? And then we get to the definition, which is what I want to write down. So here we go. I'm assuming that the reason that like that the Rademacher and the Walsh functions are in here is that they surely must provide an example of something. If I had to guess. We'll see. So separable spaces. Separable spaces. All right, so separable spaces. Hilbert space is called the separable. If what? If it contains a complete orthonormal sequence. So to say a Hilbert space is separable is just to say it has an orthonormal basis, is that right? He says finite dimensional Hilbert spaces are considered separable as well. Right. So I guess if you allow your sequence to be a finite sequence, then you don't, kind of depends on what you're, but usually sequences go on and on. So I guess it's needed to say that separately. All right. And then he starts, extolling you with the examples which are separable, right? L2 minus pi to pi, separable. The space L2, separable. What's a non-separable Hilbert space? That's his next example. He says the space of all complex valued functions on R which vanish everywhere except a countable number of points in R. What? So H is equal to F from R to C. Thank you. F from R to C such that f of x is equal to 0 almost everywhere. And f of x equals to 0 for countably many x. And such that, man, he's got lots of terms and conditions here. The sum, f of x not equal to 0, of the the absolute value of f, well, I guess the complex modulus squared of f of x is finite. Then you define the inner product in kind of the natural way. And he says, so the inner product here is defined by fg is equal to the sum over f of x g of x, not equal to 0, right? F of x times g of x conjugate. So that's a countable sum, right? And he said this space is not separable because for any sequence of functions fn in H, there are non-zero functions f such that the inner product of f with fn is equal to 0 for all n. And that would violate the theorem we proved earlier today, which was that the inner product of a vector with xn for everything has to imply that the vector is 0. And notice it's not just for one sequence of functions this happened. It says for any sequence of functions this can be done. All right, so, well, let's see here. 1, 2, 3, 4. Yeah, I think we need another day. I'm sorry, Audric.
Okay.
I mean, this book is like, this section is like crazy long. Yeah, I better stop here for today. Sorry, guys.